All right, and then we're gonna go to lines 21 through 25 here. So with this, we're basically gonna add in the weight of the water right here. So when we spin the model, we made a base right here, and we made a base right here. Then we're going to apply water pressure to both of those faces. This will simulate. In real life, obviously, we don't just all of a sudden there's that much water in a dam. That would be awful. You know, it's slowly filled, right? But for simplicity in this case, we're just going to add that water pressure right to the faces of the dam and on the base of this. Obviously on line 23, we're just applying 500,000 units, we'll say pascals, water pressure straight down on that base. The pump should start with that. That's because this distance here is 50 meters. So water pressure on top two face would simply be the pressure would equal density, gravity, and the height of the dam. Water density is 1,000. Gravity we just set at 10. Height is 50. 5 pascals. So we're using metric. And the water pressure on this face, on top four face, needs to have a gradient because it's not all 500,000 pascals. And the gradient is basically equal to, which in almost all cases, that's what you'll use as a gradient because you're modeling things on Earth, gravitational forces. And it might be explained a little bit better in the documentation. Let's see what it says. So I just put my cursor there, and hit F1. It says apply a gradient to the scalar value provided. And if you click on this, it gives you some actual quite nice examples. Probably explained a lot better than I do. Here's the equation that it uses when using gradient. Water on the stress. This axis will be this vertical stress. And this will be like height. Basically, the stress increases as we go down. And that's actually what the gradient is. Probably more confusing than I'm making it. So I'd recommend taking a look at the documentation. And in fact, actually, I already wrote that, so can't even explain it that well. Okay, cool. So now at this point, we're going to solve the model to convergence 1.0. And I am going to use the elastic keyword, but see here, I'm not using elastic only. So after it converges, it'll change back to our strength values that we used, and it will solve again. So ideally at this stage, we know our dam is standing with water, for water pressure applied to it. It shouldn't fail, right? If it does, then we're in big trouble. So let's run that. Okay, so let's go take a look at our plot here. And you can even see if you change between dam 1 and dam 2 that the stresses have changed, which is we would expect because now there's been the force of water added to the right side of the dam. one thing I find myself doing a lot when I'm modeling is I look at contours a lot because that's the most useful information, but a lot of times we'll also look at the state. And the state shows the state for each zone. And the coloring will be based on your constitutive model. So remember the base is all elastic, so it will always say none. There won't be any failure because it's elastic. But you'll notice over here that there's one tiny zone that failed in tension. Tension dash P means it failed in the past. So remember, this is like continue, like time marching, or so at some earlier time, that zone had failed. But what typically happens in really big 3D models is you'll just initialize the stresses, and you'll find all sorts of zones along the surface are always in some sort of failed path state. It doesn't mean your model's failed at all. If we're looking at this and we saw that there was a bunch of failure on, going through the slope, and it said, and it didn't have the dash P, that means it's failing now, and now we know something's wrong. So a lot of times people will look at a model like this and like, look, it failed in the past, one zone. It must mean the whole model failed. No. Okay, so that's a label.